We go inside the picture. Yes, yes. Oh my goodness.
John is a joiner, right?
John?
Yeah, like
Yeah, I think so. Yeah. He's done everything except for like sign.
sign. I see. Okay.
I think yeah, we'll have like a lot of people said yes already.
Yeah, right. Like, I feel like we're getting a bunch.
Yeah.
I feel like Ted and Noah will like this.
Yeah.
Yeah, we're not in a.
Yeah. We're being surveilled right now.
Yeah, everything's right.
Oh, all right. So, hey everyone, welcome back from spring break. So today we're gonna start a new unit or component of quantum cryptography. So basically, for the next little bit, I'm just going to give a high-level overview of, first of all, what is cryptography about? Some of you are taking a crypto class, but maybe others are not so familiar. Then I'll talk about what the landscape of quantum crypto is like, and then we're going to focus on a specific sub-area. So, like broadly speaking, what is cryptography about? It's about honest parties who want to communicate or compute in ways that are secure against adversaries. So, and there's many different ways in which, what do we mean by secure, and so on. And that's sort of like where the all the details come out. But the most, one of the basic tasks that you'd like to do in cryptography is, you want to send a secret message over to someone, and you want no one else to know what that secret message is. It's a very basic task. Another task you'd like to do is maybe a bunch of us want to, we want to compute some function of our secret data, and we want to like all see the output of that function, but we don't want to leak our secret data to other people. And that's something else that cryptography allows us to do. So these are the types of things that people think about. So with this in mind, a very useful way of kind of organizing classical versus quantum crypto is in the following way. We'll sort of categorize whether the honest parties and adversaries are quantum or not quantum. Oh, by the way, I think we need, who hasn't scribed yet? Would you two be able to scribe? Yes, maybe you do the first half and you can do the second. Thanks. And what's your name? Yeah. Oh, wait, Joan. Okay, yeah. So honest parties here, adversaries here, and we say whether they're classical, classical or quantum. So when both the honest parties, like the people who are actually trying to send a message or compute something securely, are classical, and you're worried about adversaries who have classical computing power, or they only know how to manipulate classical information, then this is the domain of classical crypto, classical cryptography. Maybe you want to call it traditional crypto, like this is what 99.999% of cryptographers study, because it's the most relevant setting. Okay, what if we're talking about honest parties who are classical, like you and me? We still run, these classical computers, but we're worried about adversaries who might possess a quantum computer, maybe NSA or some sophisticated organization. They've built a very powerful quantum computer, and we would like that our crypto systems are still secure against those types of adversaries. This is known as, the study of this setting is known as post-quantum cryptography, right? Is sort of in the era where we're past the point where someone has a quantum computer. This box right here, where the honest parties have quantum capability, but the adversaries don't, is uninteresting, because in cryptography, you're usually very paranoid and you're worried about adversaries who are at least as powerful as you are. Okay, so we don't really think about this setting. And then finally, this last box is a world where everyone has a quantum computer. You have a quantum computer, I have a quantum computer, our adversaries have one. And we want to take advantage of the ability to process and transmit quantum information. So here, there's no like universal term for this, but I like to call it like fully quantum crypto. Where you want to do things in this setting that might not even make sense or have any analog in the classical setting. So the thing that I really want to focus on is a fully quantum crypto, because I think that's more interesting, at least in my opinion. Of course, clearly the post-quantum crypto stuff is super important, and I'll say a couple words about that. Okay, so before we jump into this last box, let me say some things about post-quantum crypto. So probably most of you know that once we build full-scale, large-scale, fully fault-tolerant quantum computers, then we can run something known as Shor's algorithm, which can factor large integers in polynomial time. And this would be really bad news for the current state of things, because the most widely used crypto system known as RSA, its security assumes people aren't able to factor large numbers quickly. So clearly, we're going to have to find some replacement for RSA, and that's what people are trying to do. I should just write this here. So a big part of this area, it's not all of it, but it's a big part of it, is to find alternative crypto systems for classical computers that are resistant to quantum attacks. So currently, actually at QIP, which is the conference that some of us were at a couple weeks ago, there was a really, really nice tutorial, and there's a video online that I'll post a link by an expert in this field named Chris Piker, who is explaining the state of this goal. And right now there's a competition that's being run by an organization known as NIST, the National Institute of Standards and Technology. And this competition it's been running for a few years now. And they've invited people to submit proposals for crypto systems that are not RSA, that are plausibly secure against quantum computers. And it's sort of in the final stages. It's like in round 3 of this competition. So initially they had like a large playing field of many different contenders, but a lot of them got broken. A lot of them have some flaws in them, and it's been whittled down to just a handful. Okay, and these are sort of the final ones. And the hope is that once they decide upon a standard, that companies like Microsoft and Google will just replace all of their RSA code in like your Chrome browser and just push an update, and without you noticing, your browser will use a crypto system based on some other hard problem. Okay. And the most promising candidate for such alternative crypto systems are ones based on something known as lattice problems. Okay. So
when you say a competition, you mean like practical systems?
Practical systems.
Real systems.
Real systems, yeah.
Okay.
So actually that's kind of a very important criteria of this competition. Like they don't just want to have some theoretical argument that, oh, these crypto systems are secure, but they want to make sure that they run quickly, they're practical, you can implement them. They don't have like subtle security flaws and so on. So RSA, it's assumes hardness of factoring. So a very prominent post-quantum suggestion proposal is so for PQC's post-quantum crypto, use something like hardness of solving lattice problems. Okay, so a couple words about that. What are lattice problems if you haven't seen them? So basically, the input to the problem, it's a mathematical problem where you're given a description of some discrete lattice. Okay, so you're given a bunch of points. These are, let's say these points are I mean, this is 2 dimensions for now, but let's imagine that you have points in the integer lattice ZD, and you have some finite subset of like periodic set of points. Okay, they form a group. Okay, so let's say this is the lattice, and you have points like this. How are you given the points? You're given some linear basis for the points. Okay, you're given some matrix that kind of specifies how you get these points in space. All right, and given this basis, your task is to find the shortest non-zero point in this lattice. Okay. I mean, when you look at the picture, it's kind of obvious. Like if this is the origin, you say, well, maybe this one's the closest. But if you're just given a basis, it's often not clear what's the shortest vector. So the assumption, and this is not something that we can prove, but we have evidence for, is that finding the shortest vector in a lattice is difficult, not just for classical computers, but also for quantum computers. So that's sort of the basis for these post-quantum crypto systems. And people try to build encryption schemes, signature schemes, and so on. That if you break them, then you found a fast algorithm for breaking this, but you assume there is no fast algorithm. That's kind of, yeah.
In this scheme, is there like a notion of like what the 2 honest parties have and like what they share that enables them to compute this quickly? Or like is there an analogous, or is there an analogy to like traditional systems where there's like a private key and a public key?
Good question. So you're basically asking like how do I go from here to an actual like way of encrypting or decrypting messages? So that's not there's several steps. So there's several reductions, and yeah, I guess I mean, I'm not an expert in this, so I won't be able to describe it. Yeah, it's not obvious like how, what's the corresponding between this and certain messages. I can say, actually, I can say one thing. So what's one step of this reduction? So this is a lattice problem. So the problem that people think about is something called the shortest vector problem, right? It's this thing I described. There's a reduction between the shortest vector problem and something known as learning with errors. And this learning with errors problem is much closer to the crypto system part. So here, essentially, you imagine that someone chooses a random matrix. And let's say it's a random integer matrix. So let's say it's m by n. Okay. I think actually it's usually over some, it's like mod, integers mod some number q. And someone picks a random secret vector s. Okay, this is your secret. And imagine that you're given this matrix A times S, right? So this is a vector. And if I just gave you this vector, if A is invertible, then you can solve for S, right? That's an easy thing to do. But we want to make this harder. So you say, let's add a little bit of noise. So what you give to someone is not A times S, but AS plus some vector that has randomly chosen entries, that's small enough magnitude, and you give them this. And the assumption in this learning with errors problem is that it's difficult to recover S. So this noise scrambles things. Okay, and then once you have this learning, so what's known is that if you can solve the learning with errors problem, you can actually solve the shortest vector problem. And then from here, it's maybe it seems a little easier to construct some sort of crypto system, including encryption or signatures or something.
What is the state of the art regarding things we know how to build from learning with errors? Like, can we do I/O from?
That's a great question. So we can build an amazingly large number of different tasks from LWE. We can't quite get I/O from it. I mean, LW is a big part of I/O is obfuscation, so it's like some very fancy crypto primitive. Currently they need LWE plus some other assumptions. What's interesting is that there's currently a big open question is, can we achieve I/O from post-quantum assumptions? Anyway, so yeah, that's the post-quantum stuff. And yeah, it's very
Is that
practical.
something that people can achieve using classical crypto? Is I/O thing?
It's purely classical. I mean, currently there's no quantum resistant I/O that's
Like it uses elliptic curves and things like that.
it uses like what do you call it? Like yeah, stuff that's related to factoring, I think. It's kind of, I mean, it's so new that like right now they only know how to accomplish it under a hodgepodge of different assumptions.
It's like four assumption.
Yeah.
Call, yeah.
Something like that. Okay, but anyways, this is not the thing we wanted to focus on, but just to give you a little snapshot of what this world looks like. But instead, we're going to talk about fully quantum crypto. You know, we're fast forwarding, and 50 years in the future, 100 years in the future, everyone has a quantum computer. Everyone's sending quantum states to and from each other. Can we take advantage of things like no cloning, monogamy of entanglement, the uncertainty principle to do cool stuff that like classically just doesn't even make sense? That's what we'll talk about. All right, let's turn to that. So the first thing, so today we'll talk about two different instantiations of this fully quantum crypto. The first is something called quantum key distribution. And the second thing is something called quantum money, which I'll talk about in the second half of today's lecture. So quantum key distribution. The task that this is trying to solve is that we have two honest parties. We call them Alice and Bob. Bob. They've never met each other before, but they are connected by a communication channel. So actually they're connected by two communication channels. One is a classical channel where you can just think of this as they can call each other over the phone. And it's an authenticated channel, which is sort of necessary. This means that Alice knows for sure she's talking to Bob and not some other person, right? I mean, if you don't have that assumption, then kind of it's impossible to do any reasonable cryptography. Like, if you're not even sure if you're talking to your enemy or not. Yeah. So you just assume that you have some authenticated channel, but this channel is open to the public. Like, someone's listening in on the conversation. They're also connected by a quantum channel, meaning that using this link, they can transmit qubits back and forth from each other. So they have these channels, and their goal at the end of the day is they want to have some sort of conversation, send some qubits back and forth. And they, at the end of the day, they want to agree on some sequence of bits called a key.
Is the quantum channel also public?
Yes, everything is public here. So, so sitting on the channel is some adversary that we call Eve. So Eve, for just to keep things simple, let's imagine that Eve is just passively listening on the classical channel. Like she can listen in everything that they're saying to each other, and she can tamper with qubits that are sent back and forth on this quantum channel.
But not on the classical one.
Yeah, let's just keep it simple, not on the classical one. So, they're talking, and but at the end of the day, they want to, both Alice and Bob want to generate some random string, uniformly random string of n bits, say, that only they know and Eve has no information about. Like from the point of view of Eve, K is just a uniformly random string that she doesn't know anything about. Right, so once they have this, then they can do all sorts of nice crypto, like they can send secret messages, things like that. Okay, so that's the goal. And it's like secure against adversary because adversary has no information. Good, so this is something that people do all the time today. Key exchange is like a very important part of today's crypto systems, but they all require computational assumptions. Meaning, like for example, RSA, it's this public key crypto system, and it allows Alice and Bob to do the same thing. I mean, without the quantum channel, it's just a classical crypto system. But like I said, it assumes that Eve is not able to factor large integers. But if Eve has a quantum computer, she can. Quantum key distribution says that if you allow Alice and Bob to send qubits to each other, then it doesn't matter what type of computational power Eve has. She can have the most powerful quantum computer in the universe. She can have infinite amounts of computation time. But because of the properties of quantum mechanics, their key will be secure at the end of the program. So this quantum key distribution allows for information theoretic security, or in other words, it's unconditionally secure. So CKD, which is quantum key distribution, enables this with unconditional security. There's no, aside from assuming that you have this authenticated channel and so on, then you don't have to assume anything about the capabilities of Eve. Like this will be secure forever. This is also, one of the oldest applications of quantum information and one of the most mature. Like people have built quantum key distribution systems. It's commercialized, so it's actually it's a real life thing, and people have actually deployed it. So let's see how it works. I'm going to describe the kind of the original protocol for this, known as BB84. This is called this because it was invented in 1984 by Charlie Bennett and Gilles Grissard. So I'll describe the protocol and then I'll get into the intuition for why it sort of plausibly works. So there's a bunch of steps. So I should spread this across a couple boards. So I'll move over here. So Alice. So Alice is first going to pick two random strings. So she's going to pick two strings X and B that are, say, n bits long. And then she's going to generate a sequence of qubit states. So she's going to send a qubit psi I that's equal to the following state. So xi is the ith bit of the string x. Okay, it's a state in the standard basis. And then think of B as specifying a basis. Okay, it's an n-bit string, and for each bit, for each location, it's going to specify 0 or 1. And if it's 0, then it's going to send xi in the standard basis. If it's 1, then it's going to apply a Hadamard and send it in this 45-degree angle basis. So it's rotating. So this qubit is going to be one of 4 possible states. It's either 0, 1, plus, or minus. And this gets, for each I, this gets sent over to Bob. Okay, and then step 3, Bob has no idea yet what these two strings are. So he's going to pick his own. He's going to pick Q prime randomly, another n-bit string. And then he's basically making a guess for the basis settings of each of these qubits. Okay, and he's just going to blindly measure all of these qubits that he's received in that particular basis. So he's going to measure psi I according to basis bi prime, which is his guess, and then he stores the outcome as xi prime. Another way of saying it is that if bi prime is equal to 1, then he applies a Hadamard and then measures in the standard basis and then stores the outcome as xi prime. So Bob now has strings x prime and b prime. And this concludes the quantum part of the protocol. After that, everything they do afterwards is classical. So before I continue, just let's imagine what's happened so far. On the locations where Bob's basis choice agrees with Alice, then it should be clear that xi prime is equal to xi, right? And otherwise, for the places where they don't agree, what is the relation between xi prime and xi?
They can be equal in probability half.
Yeah, it's going to be equal with probability half and not equal with probability half, right? So it's totally independent. Good. So, at least, some of only they knew where their basis choices agreed, then they would have synchronized strings that were identical. And they could possibly use that as shared key. But of course, they don't know where, they have to figure out where those places are in a way that doesn't leak too much information to Eve. So that's what the next phase of the protocol is going to be. So step 5, they're going to actually exchange.
What is step 4?
Oh, step 4. This is step 4. Indexing. 4. Then they're going to exchange basis information, all in the clear. So this is over the classical channel. Eve can see everything. Send B to Bob. Send B prime to Alice. And they're going to just drop all the coordinates where they disagree. And roughly speaking, like they're going to drop half of the coordinates, right? Because in half of them they'll agree, half they'll disagree. So, you know, roughly n over 2 coordinates remaining. All right, and now they're going to check. Like, so if Eve didn't do anything, in all the remaining places, xi should be equal to xi prime. But what if Eve did something? So what if she tried to tamper with the qubits, try to extract some information? So the rest of these steps are going to try to detect this. So they're going to sample a small subset of surviving coordinates in their x and x prime strings. And check if in those in that small sample, if xi is equal to xi prime. So by small, think of it as, I don't know, like 10%. I'm just making numbers here, but to give you an example. So 10% of the remaining n over 2 coordinates, they're just going to say, you're going to pick it and over the phone, just compare notes. Does xi equal xi prime? If there's any disagreement, then they'll just say, let's try again, right? Something's happening on the channel. So you're just going to stop the protocol. But if everything checks out, then they're going to assume for the remaining 90% of these surviving coordinates, things must match, or mostly. Okay. So they're going to trust that for remaining, say 90%, the 2, xi is equal to xi prime. You know, for most of those coordinates, maybe not all of them, because maybe they were unlucky and there was one xi that differed from xi prime, and they just didn't sample it. But that's okay. They have good confidence that most of these coordinates will agree. And then over here, then the final step is they're going to perform several processing steps. They're going to perform something called reconciliation, where they're going to run some protocol over this classical channel where they try to fix up any of these remaining errors. Okay. Remaining errors. Okay. So by this point, Alice and Bob will have 2 strings that match exactly. Which is good, except Eve Eve might have a little bit of information about these two matching strings, right? Because when they perform reconciliation and they do this small sampling, Eve is listening to their conversation and she might deduce some non-trivial pieces of information about the two matching strings they have at this point. But they match, and the final step is they can then do some, essentially some sort of hashing idea where they sort of hash down their strings to kind of clear out any information that Eve would have about the two strings. So this is called privacy amplification.
Is like with no communication?
No, all of this requires
Oh, okay.
communication. But yeah, so I'm being very high level and hand wavy here, but it's just to give you a feel for how these protocols work. Right. So in 7, they do some communication. They're like basically comparing parities of their different strings. If they notice an error, they'll try to fix it. Okay. But Eve also hears these parities, so she knows some information about these two matching strings. So then they do another step where then they kind of like take different parities, like they say, we're going to take parities of bits 1, 10, and 100, combine them, consolidate them, and they're just going to scramble up their strings in some synchronized way that basically at the end of it, Eve has no idea what strings they have left. And each of these protocols actually are like research areas in themselves. They get very complicated, but people have come up with really clever ones to do it. Yeah.
Is the privacy can Eve know what the privacy amplification procedure is?
Yeah. She knows every single step of this protocol. Right, like she's studied BB84 just like we have, but after the end she doesn't know what strings. So that's kind of an outline of the protocol, and for the remaining like 10 minutes or so, I want to give you some intuition for how could this possibly work, right?
Like, it is crucial that 4 is done after 2 and 3,
Yes.
right? Because of no cloning.
Yeah.
Okay.
Yeah, that's a good point. Yeah, all the quantum magic is happening in steps 1, 2, and 3.
Yeah.
Everything else is classical. So let's talk about some intuition. Okay. This is just going to be intuition. This is not a formal security proof. These formal security proofs get very involved and take decades of research. But let's imagine that Eve, in general, Eve could do all sorts of crazy things. Like she could just, each of these qubits that are being sent across, she could just scoop up and send completely unrelated states to Bob. Okay. And she could do some crazy quantum computation on them that takes exponential time. Any of that is allowed in general. But for now, let's assume that Eve does the following attack. Assume that Eve, as each qubit is streaming by, she makes a decision. She either just lets it go by, or she decides to measure it. When she measures it, she has to make a guess about what basis this qubit was encoded in, whether it was in the standard basis or the Hadamard basis. Okay, so and so let's say when if she does decide to measure it, she gets outcome yi. Right. Basically, Eve is just trying to figure out what the xi's are. So yi is her guess. Okay, but Eve, basically, what is the chance that Eve will correctly guess? So if she lets a qubit fly by without tampering, then then she doesn't know anything about that particular bit. But what about if she does decide to measure it? Well, with probability 1/2, she's going to get the wrong basis choice, right? Okay, so if Eve guesses the right basis, then yi is going to be equal to xi, right? And as she measures it and she just she puts it back in the channel and it continues onward. So if she guesses the right basis, then that qubit is not tampered with, right? Like for example, if it was plus state, right? Then she'll measure in the plus minus basis, and then it stays the plus state. Nothing happens to it. So that happens with probability 1/2. But if she gets the wrong basis, which happens half the time, then she's going to get a completely uncorrelated outcome, right? And here's the thing, if she measures in the wrong basis, then this qubit has been disturbed. The qubit becomes something else, like, let's just pick a specific situation. Let's say the qubit was actually, let's say plus. For example, psi I is equal to plus, but she chooses to measure in the standard basis. Then she's going to get 0, 1 with equal probability, right? And then
probability 1/2 she flip the bit.
then it'll be the qubit will be encoded in the wrong basis. So she gets 0, 1 with equal probability. Then psi becomes, let's say she gets 0.
You are assuming that we start with plus.
Yeah, let's say we start with plus.
Okay.
Like the true thing was plus. She measures in the standard basis and she gets 0 with 1/2 probability. And now psi I collapses into plus. And that's what gets sent to Bob. So, okay, so she can do this for each qubit. Now, what happens then later in the protocol? So,
Actually, if it collapses to 0, like she is fine, right? Like because they will still agree. No,
Not quite. So let's imagine now we move on to the protocol.
It depends on the guess.
Yeah, so
Okay.
suppose now for this specific I, suppose Bob bi prime is equal to 1, right? Bob also thinks for this coordinate that it should be in the Hadamard basis. So he measures in the Hadamard basis. So Bob measures psi I, which is now the 0 state in the plus minus basis. He's going to get a totally random outcome. He's going to get a random outcome x hat prime. And then when Alice and Bob are comparing notes, like maybe they sample a small subset of these remaining coordinates, and they also decide to check this, they're going to see that they disagree. So basically, you sort of like multiply all these probabilities of each of these things happening. And then for this particular coordinate I, there is basically a 1/8 chance Alice and Bob will notice a discrepancy. Well, maybe it's not exactly 1/8, but it's some number. It's kind of like 1/8. You know, you have all these probability a half of various things happening, and also the probability that you sample the right subset. But it's, anyways, the point is it's some constant probability they'll notice something's wrong. And this is for each qubit that Eve decides to tamper. So what happens is Alice and Bob, they're doing these checks, and if Eve decides to tamper with a significant fraction of qubits, then Alice and Bob will notice something's happened, and they'll just abort. On the other hand, if Eve lets most of the qubits fly through, and she only tampers with just say 1 or 2 qubits, that's totally okay. Like maybe she knows a couple bits of information, but because of this reconciliation and privacy amplification, all of that information Eve has extracted gets hashed away. It gets sort of erased. So that's kind of why this protocol works.
Like she can do more complicated things than this, right? Like, yeah, for sure.
Yeah, she can do some complicated thing on all the qubits simultaneously, but actually the security proofs kind of try to reduce to this case at a high level.
And like there's she cannot learn X, but she does have the power to make them always abort, right? It's like
Yes.
It is not good. Like I want something in practice like that. Even though people are listening to me, I still want to do things. So like this protocol is not optimal in that sense, right?
Sure. Basically, you're saying you can't prevent a denial of service.
Yeah.
But I think that's always like even in any protocol.
Yeah.
If someone just snips your communication cable,
Oh, okay.
then-
Okay. Yeah.
then
Yeah.
you're
Okay.
screwed.
Yeah.
Yeah. At least someone's trying to
Yes.
make your life difficult. Is there another question? Yeah, another thing I want to mention is that in some sense this intuition also takes advantage of the no cloning principle of quantum states. Like imagine that cloning of quantum states was possible, then Eve would just make zillions of copies of psi I, and then she could totally find out, she would just keep on measuring and say, oh, I think this is a plus state. And then she would know exactly what state it was. But she can't clone because trying to clone or measure it would disturb the state. Okay, so that's kind of the high level of BB84. Yeah, any other questions? All right, so let's yeah, take a break. Maybe let's come back in 5 minutes. That's it.
Wait, Henry, good question. Wait, so here we just like send the qubits over,
Yeah.
and then we have like this no clouding guarantee. But then how do you do this in like the classical case?
How do you do the?
How do you like do like key distribution in the classical case where like maybe your adversary can't copy like any like bits you send over?
I don't think there's classical key
Oh, yeah,
distribution.
this is not possible. Like
Oh, okay.
you have to use computational assumptions. Then you use like RSA and stuff like that. Yeah, so this like unconditional security only happens in the quantums.
Like there has been a lot of work on QKD sense,
Oh, yeah.
right? But like,
Oh, yeah.
what is there to improve here?
Oh, many things. I mean, so first of all, this protocol is very inefficient.
I
Like,
see.
you know, you do tons of communication, and at the end of all this privacy amplification, you get like a tiny key.
Mhm.
Another thing is that this protocol, as I've described, is not noise tolerant. Like maybe there's no adversary, but there's just noise, I mean, which is always natural. And so of course there's going to be some flipping of bits. And so you don't want to reject just because there's been some innocuous noise. But you want to distinguish between what's noise and what's an adversarial attack. And so the protocols get more complicated.
I see.
And then there's also like manufacturing these things and how do you engineer them?
A quick question about the projects.
Yeah.
When are they due?
So the last 2 weeks of April, or whatever the last 2 weeks of class are, there will have project presentations. So when you have a presentation, that's when the presentation's due. And then there's a write-up that's due at the end of April.
Is there hope of like showing that more cryptographic stuff can be it can be done like information theoretically secure in the quantum world? Question make
does.
sense.
Yeah, that's especially after this came out, they're like, well, maybe we can do everything. So there's lots of impossibility results. Like a lot of there's things where you can sort of do information theoretically, but not. Like for example, there's the task of coin flipping.
Mhm.
It's like, you know, let's say you and your friend want to agree on a random coin toss, but you don't trust your friend. Like maybe they'll try to bias it in their favor or something. So there are crypto protocols where you can do this, but it requires computational assumptions.
Commitment schemes?
And yeah, commitment schemes, also commitment schemes. And people say, well, maybe with like, you know, BB84 like ideas, you can do that unconditionally. And the answer is you cannot, not perfectly. You can sort of do coin flipping where the most, like you can guarantee that your friend can't bias it too much in their favor, but not perfectly.
Let's assume that the classical channel is authenticated. So how is that authentication? If this is supposed to be information theoretic without any assumptions,
Yeah.
then how is the classical authentication implemented?
Oh, that's no assumptions after you assume there's an authenticated channel.
Okay.
Like no computational assumptions.
Yeah, no computational sessions. I mean, in practice, you set up authenticated channels using computational sessions.
I see. Okay.
But yeah, somehow authenticated channels are like, if you don't have them, you don't have anything.
What do you mean by authenticated channels?
Like, if I call you on the phone, I know I'm talking to Dean and not someone who's pretending to be Dean.
You don't though.
Yeah, I guess I don't.
Yeah, yeah. Like for most of the interesting primitives, it is known that like you cannot do them quantumly, information theoretically secure.
Yeah.
Homomorphic encryption and such.
Although now there's this interesting thing was maybe you can use weaker assumptions or different sets of assumptions in the quantum setting.
I see.
This is something we'll talk about next week. Yeah, so this. You guys are still doing quantum money, right?
Me and Dean, yeah.
Okay, so hopefully those won't step on your toes. This is sort of just very basic background. Huh?
You're helping us.
Yeah, okay, good, yeah. So you can get to the good stuff when you present. Yeah. Okay, so let me talk about quantum money. This is another very important thing in this area of fully quantum crypto. And actually, there's a nice story about quantum money. Before I even explain what it is, so in some sense, quantum money is, I said BB84 is like one of the first quantum info things that were studied in the 80s, but quantum money even predates that. So there's someone named Stephen Wiesner. Who was a physics graduate student at Columbia back in like the 60s. And he was studying physics and he came up with this crazy idea known as quantum money, right? And basically the idea is, use quantum states as a way to create a new type of currency that's not clonable. And this is so way ahead of his time. And he wrote this paper, he called it conjugate coding. And he sent it around and no one was interested, right? It was just, he sent it to journal after journal, it was repeatedly rejected. And after a while, he just sort of gave up and left academia. Okay. It's kind of a sad story, but a couple things. So eventually, Steve Wiesner just sort of hung around New York City and he was friends with Charlie Bennett and Gilles Broussard, okay? And he shared, he's like, oh, I have this paper that I worked on a long time ago and no one was interested. And then Charlie Bennett took a look at it and was kind of inspired. And it was this thing that inspired him to come up, and Gilles Broussard to come up with BB84, with QKD. Okay, and then Charlie Bennett and Gilles Broussard knew how to popularize it and create interest. So that's why we know about BB84, but not so much Stephen Wiesner. And that's almost the end of the story, except what happened to Steve Wiesner. He left academia and he decided to become a manual laborer in the deserts of Israel. So he moved to Israel, and so no one ever saw him again, except he was just sort of.
Where in Israel do you know? I don't know.
I don't know, but I'll have a personal story. So a few years ago, like in 2016, I went to Hebrew University in Jerusalem. And I was giving a presentation, and there was like someone in the back of the talk, and there's people like Rita Harnav and Michael Ben Orr and all these like famous people, and there's this guy who honestly looks like a hobo, like he's just like very long beards, like very shabbily dressed, but he was asking the most interesting questions out of everyone in my talk. I was like, well, who is this guy? And then Dorit was like, that's Steve Wiesner. And it's like, wait, the Wiesner? Like I thought he was, passed away or something, but that was him. And, he was, apparently he showed up to these seminars and just out of interest. He doesn't do any research anymore. But at the time when I met him, his hobby was to build really powerful homemade lasers just for fun. And like when he mentioned this, or like Dorit mentioned this, and he was like, oh yeah, I can show you. So he opened up his backpack and brought out this like huge contraption. He's like, I built this thing. And then Dorit was like, just put it back in the backpack. Because you accidentally blind someone. So that was my encounter with him. And unfortunately, he passed away last year. But yeah, but in some sense, his paper it kind of started off quantum information. This idea you can use quantum states to do interesting information tasks. So that's sort of a bit of history. Yeah. So what did he come up with? Let's think about normal money. So one undesirable or problematic issue with current forms of currency, whether we have like physical dollar bills or digital currency, even blockchain and things like that, is that the hard part is you want to prevent someone from copying it, right? Like if you have a unit of value, someone can't just copy it endlessly because then the value would go away. And no, in principle, like if you're given unlimited resources, all currency or all classical currency is copyable, right? Like if you could scan a dollar bill atom by atom, you could make a perfect copy of it. That's indistinguishable from the first. Quantum money is to say, well, let's take advantage of the no cloning principle to create forms of money that cannot be copied. So this is currency that satisfies clearly non-clonability, right? Even if you had all the resources in the universe, you still cannot make an exact replica of a quantum dollar bill. But of course, non-clonability is not enough. Like I can give you a hard random state that's non-clonable, but it's also not currency because you want to verify that it's worth something. So it also has to have the property of verifiability. Right? Like you want to verify that a quantum state that was given to you was actually minted by an appropriate authority or like the government or the bank or something like that. So that's what quantum money is supposed to, you want to satisfy these two properties and how can you do it? Well, let's talk about Wiesner's scheme. And it'll look very familiar. So it assumes that we have a central bank that is in charge of producing and distributing quantum dollar bills. And it will distribute out quantum money states of the following form. A quantum money state is a pair. It's a classical string known as a serial number. So I'll say there's a serial number S. And there's a quantum state that is a function of this serial number. And this is an n qubit state, let's say. Right? What is this f? F is a function that the bank has generated. So f is going to be, it's going to map n bits. So a serial number, this is n bits long. Or actually, no, it's not n bits long. It's some number of bits long. Oh, sorry. Actually, it doesn't really matter. Okay. It's, let's say it's m bits. So it maps m bits into a sequence of 0, 1, plus or minus to the n. And this is a random function. That's held in secret by the bank. Basically, for every possible m-bit serial number, it has a sequence of 0, 1, pluses or minus that it decides. And you can imagine what this is supposed to mean. This state, given serial number S, will be this either 0, ket 0, ket 1, ket plus, or ket minus. So it's equal to f of S1, S2, and so on. And so it's just going to be a collection of qubits, each in the standard basis or in the Hadamard basis. And that's it. These are the quantum money states that are distributed out. So and people, the populace gets them. But it's very, very important that this function f is kept in secret. Okay. All right, so now let's see, or kind of see why it's non-clonable or why it's verifiable.
Oh, wait, like, that's it?
That's well, I haven't said how you verify it by it,
Yeah.
but it's going to be pretty simple to see. So let's say Alice wants to buy a coffee from Bob. So Alice gives Bob one quantum dollar, one quantum banknote, and Bob needs to check that it's not some random state that she's generated. So he's going to, and he has a serial number, so he's going to say, hold on a second, I'm going to go to the bank and double check this is a real quantum dollar bill. So he goes to the bank, and the bank looks up the serial number in their secret database. They compute this function f, and they see whether it's in the standard basis or in the Hadamard basis. So they will measure each qubit according to the correct basis and check whether this state is really this. So bank will measure each qubit of supposed banknote and check matches f of s.
So each time I want to buy a cup of coffee, I need to go to the bank.
Yeah, well, with this scheme, so it's not quite practical. But I could also sort of say, hey, it's not much more practical with Bitcoin.
Yeah.
That also takes a few hours, right?
So like today's money, nobody verifies
Yeah,
anything.
true.
Well, sometimes, the cashier will be like, the light and, yeah. So that's the verification. And you can sort of see why it makes sense, right? Like if the general populace, if Alice doesn't know this F, then she kind of has to guess for each qubit what the correct basis is. And if, she's going to be wrong in most of them. So that's verification. And then what about non-clonability? It's also non-clonable because we know quantum states in general are not clonable. Right? It's not like you can't do tomography because you only get one copy of each qubit. Right? If you measure that qubit, then if you guess the wrong basis, it would just collapse and then that's it. Qubit's gone. But people have done, actually, it's interesting. He proposed the scheme back in like the late 60s, but it was only a few years ago that people tried to give a rigorous analysis of the security of the scheme. Like, you want to argue that what's the maximum probability that Alice could make 2 copies of her quantum banknote? So there's a recent result due to Molina, Vidic Watrous. From 2012, that shows that the optimal probability of cloning, of successfully cloning a quantum banknote a banknote is 3/4 raised to the n. Okay. So as n gets large, this is going to be exponentially small. So basically, it's impossible to perfectly clone a banknote. And if you use the intuition that really the best that Alice can do is to guess what basis things are encoded in, and she'll get it wrong half the time and so on. That is actually not the optimal attack. There's a smarter attack you can Alice can perform, but it doesn't do much better. And they showed actually for each qubit you can only do probability 3/4, and then there's n qubits, so you succeed with this probability.
They show this is like the best.
Oh yeah, and this is optimal. Yeah, so they give an STP. Yeah.
Sorry, if we're guessing the basis, aren't we going to? Oh, sorry. Okay, it doesn't reach 3/4. Sorry, I was.
Yeah, it's like 5/8 or something. Yeah. Yeah, with probability half you get the basis right, so then fine. With probability half you get it wrong, but yeah, then another still 3/4.
No. With probability half, you guess the right basis,
Right.
then the bank will never know. And with probability half, you guess the wrong basis. But the bank, when it does the measurement, it can.
Oh yeah, it collapses into the right
Collapses
thing.
to
Yeah. Good. So that's 1/2 plus 1.
1/2 plus 1/4.
Wait, is that 3/4?
Wait, that's
That is
3/4.
Oh,
No, but he's saying that for one qubit, you cannot get 3/4.
It's not really cloning it. It doesn't get through the verification.
Oh, yeah. It's
Oh,
only
yeah, that's
verification,
right.
it's not cloning.
yeah, this is that's true. This is a stronger thing. This is like
Yeah.
you actually want to have you want to clone it. Yeah. Because what you described is sort of you're just talking about a way to fool the bank into
Yes.
accepting.
Isn't that the number 3/4 parent?
That matches. But we're talking about two different tasks. One is you want to submit some state that's not necessarily this state that the bank would accept.
Yes, that is what I'm talking about too.
Yes, that's what the other thing I'm talking about, which is cloning, which is I want to, starting with one copy, I want to create 2 copies of this state. So that's slightly different.
Is it somewhat similar to CHSH? Like if I have like multiple instances, I can do better than just solve each one.
Not in this case.
In
Here,
this case.
they show that for a single qubit, that 3/4 is the best you can do.
Mhm.
And then when you
Oh,
consider
okay.
SDP, it just
Okay.
tensorizes.
Okay.
Yeah, so this is one analysis of security. But there's still some issues with this scheme. So this is if you wanted to like just in one shot attack the scheme by creating 2 copies. But there are also these interactive attacks which are are problematic. So imagine that. So here is like one thing that I haven't said is when you do the verification and you walk up to the bank and you give them a banknote and you ask them to verify it. Suppose that they say this is not a valid banknote because maybe one of the qubits was wrong. What do? Do they give you back the banknote? Do they call the police? Do they give you a fresh banknote? So depending on how you model the bank, there's actually some problems. So imagine that the bank was kind of naive and they said, sorry, one of your qubits is wrong, but here's your quantum state. You can actually use this to clone the banknote.
Yes.
Okay, can anyone see how?
Uh,
It sounds like you can
that
see.
Bank, when it does the measurement, it automatically changes to the state where it is measuring in.
Uh-huh.
So doesn't that give us the information of the states of the basis it measures in?
But you don't know, I mean, they just say, sorry, we've rejected, here's your state back. Here are your n qubits.
Try multiple times on the same basis and see which ones change and which ones don't.
Yeah, we can keep going to the bank and then keep giving it the same note and then get more information about the basis.
But you don't get any, information, right? They just say no.
Yeah,
You have
well,
no idea.
but you could have guessed wrong, but there's still some probability they would say yes.
Well, if you change, like maybe change your quantum state in a different index every time and give it, like, keep doing it and see if they like accept it on each one if you do that enough times.
Exactly, yeah. So you guys, you see, so basically, you know, you have these n qubits and you say, I have a valid banknote. I'm just gonna put the first qubit aside and put a random qubit in the first slot. Walk over to the bank, do they accept? If they accept, if they reject, then you say, oh, well, that's too bad. Let me try again. And then you keep on doing that until they accept, which will happen with probability of half at some point. And then what do you know about the first qubit? It must be collapsed into the correct plus minus 0, 1. And then now you have 2 copies of the first qubit. So you keep on doing this for the second, third, and so on until you've made 2 copies of this. Of course, there's easy ways around this. Like you say, well, the bank, if they notice that you're trying to do this again and again, then they'll call the police. Or they'll just issue you, they'll just trash this and issue you a new banknote. Good. Okay, so you know, there's easy ways to fix that. Yeah, but there's still like you know, this is an interesting scheme, but this is far from practical. And one is you always have to go to the bank to verify it. Wouldn't it be nice if you didn't have to do that? If there was sort of a generally that anyone could verify that something was a correct banknote. And this is going to lead into something that Yuval and Dean are going to talk about in next month, which is something known as public key quantum money. And this is like a big area of quantum crypto research now, which is where the bank, not only does it distribute these banknotes, but they also distribute a open source program, a quantum program that anyone can run to check whether a state is really a valid banknote. But then the difficulty is, how do you ensure that someone couldn't reverse engineer this open source program to produce banknotes of their own? And that's the whole difficulty of public key quantum money. And this coming up with schemes for this actually relies on very, very modern tools from cryptography, from classical cryptography to try to accomplish this. So this is a really interesting area of research.
Like, me and Dean have like, maybe this exists, but what if I don't even want a bank, like a distributed quantum money?
Like quantum blockchain.
Yeah, people doing that?
I haven't seen a paper, but if you wrote a paper like that, it would get a ton of news.
I see, okay. I don't know. I'm just-
Yeah.
Uh,
Yeah, you'd be all over, you know, you get double the VC funding and
Yeah.
things like that. Yeah, so stay tuned for that. I think that's pretty much what I want to mention. And it's so interesting. This is sort of the starting point for this fully quantum crypto. You know, this quantum money thing has no classical analog. There's no such thing as non-counterfeitable classical money. So this is something we want to do in a quantum setting. But this is only just the beginning. There's lots of other tasks that people want to do with unclonable quantum states. Like nowadays, people are working on things like unclonable encryption, quantum copy protection. Like, what if you want to encode your favorite computer program, even if it's a classical computer program, into a quantum state, such that you give someone the state, they can run the program, but they can't make 2 copies of it so that their friends can also run them. This is an open question. Things like one-time signatures. So you guys know about power of attorney, right? Like you can say someone has ability to sign legal documents in my name. But if you give them the ability, to do this, how do you know they won't sign, 100 or all sorts of legal documents in your name, right? You sort of have to trust them. So the idea of a one-time signature is that you give them a quantum state that allows them to sign exactly one document of their choosing, but afterwards they cannot sign any other document. And you can do this with quantum states. So this is sort of the thing that people are trying to come up with, and it's kind of an exciting field because you come up with all these crazy things that people can do using quantum states.
It's sorcery, right? Like the fact that it's possible.
Yeah. Cool. So yeah, that's all I have for today. Next time we'll talk about quantum pseudo-random states and things you can do with them.